Now this is, I think I said that I was going to end these statics mini lectures before, but I just wanted to add this extra one of a spring mass because it's important when we get onto oscillating systems and stuff as a building block. So this is a spring mass system where we have a spring whose natural length of the spring is 0.3 meters, and the length of the spring is 0.5 meters with the mass, and the mass is here 5 kilograms, and where we want to find the stiffness K. Now as given, we already know that W equals 5GI because we're given the weight 5 kg, and the force H will depend on the values K, L and L sub 0, and S at we are given L equals 0.5 and L of 0 equals 0.3. The unit vector S hat is in the direction from the particle towards the center of the spring and points upwards, so it's given here, as you can see, the I here and the S here, so it's in the opposite direction. So by Hooke's law, H equals K, L and minus L sub 0 in our direction here, S hat, and plugging in these values we get 245 newtons for K, for our stiffness in the spring. Now I'll just give another example for this now. Example 2. Model spring hangs vertically from a fixed point with a particle of mass m suspended from its lower end. The particle is in equilibrium. Now we express the length L of the spring in terms of stiffness K and the natural length LO. The mass m and magnitude of acceleration due to with the mass m and the magnitude of acceleration due to g gravity. So our answer, we choose I direction to be vertically down here, and this is drawn pictorially here what we're doing with our little force diagram and our component vector, directional vector. So W equals mgi. The force exerted on the spring is H by Hooke's law again. H equals K L of 0 S hat. So we're plugging in these values now. We have a negative I for our S hat. Now since we're in equilibrium, H plus W equals 0. So by our equilibrium conditions we get this. Now jiggling around to solve for L, we get this. So this is our value for L, our length. Now yeah, this again is a statics problem, but because we're dealing with this spring now, the spring can be forced to move, and then we have an oscillatory problem where we will first go on to model it without damping, so it will just go on ad infinitum, which is obviously not realistic, and then we'll add a damping for when we get to the oscillation lectures. But this time this will probably be the last for the statics mini lectures. Now thanks for watching. Please do like and subscribe.